This is our final episode in our geometry explorations. This is part 6, in which we look at the area of triangles on a sphere. Last time we saw that the sum of the angles in a spherical triangle are always more than 180 degrees. As a demonstration, we cut a cantaloupe in half along the equator and then made orthogonal cuts through the top of the melon to get a triangle where each angle is a right angle. Notice our triangle is 1/8 of the sphere, and the surface area of a sphere of radius r is 4 pi r squared. An eighth of this would be 4 pi r squared over 8, which is pi over 2 r squared. We're going to derive a formula for this, and it's not nearly as hard as you might think. The question is, what's the area of a spherical triangle ABC? First, cut the melon in half along the line AB. That's like our equator. Now, all lines, remember, are great circles, so the cut has to pass through the center of the melon. There's my triangle ABC. Next, let's cut the melon along the line AC. Again, remember, all lines are great circles, so your knife has to tip to make that cut as if it's cutting through the center of the melon. And you get something that looks like this. And I gotta note, you can't do this in a plane. You now have a shape defined by 2 points, A and the point opposite A. So you're used to triangles and rectangles and, five-sided things. This is a two-sided figure on the sphere, and the two angles on each side are identical. So what is the area of this wedge? So instead of measuring in degrees, we measure in radians, and so the angle of the wedge we can think of as being A radians, and that's out of pi radians, which is all the way around, and so what we get is A over pi of the top half of the melon. So the area of that two-sided figure is A over pi over the whole top of the melon. In other words, it's A over pi times 2 pi r squared. The pi's canceled, and we get 2ar squared, which is surprisingly simple. Okay, so we've accounted for those two pieces, the piece inside ABC and the piece outside ABC in that two-sided figure. Now let's make the cut CB and do the same calculation for the wedge defined by the angle B. And so there we've made this cut, and the same calculation gives us that the area of that two-sided figure is 2br squared, and now we've counted the triangle again, and we've counted that back piece. For the wedge defined by the angle C, the other piece of the wedge is above C. If we worked with a whole sphere, you would see it below, but it's the exact same thing as the piece that's above it. And so there's our 2cr squared. It's the piece above C, and then we've counted the triangle again. So the top half of the sphere is the sum of all these pieces, except that we've counted the triangle ABC 3 times. So this is accounting for how we've counted the various pieces. So the top half of the sphere, which is 2 pi r squared, is the sum of all of these pieces minus twice ABC. So the area of the top half of the sphere is 2 pi r squared, and the pieces are 2ar squared plus 2br squared plus 2cr squared, and we subtract out twice the area of the triangle. And we can divide everything by 2, and we get this. And let's move the ABC to the left side and the pi r squared to the right side to solve for ABC. And we see that ABC is this. Factor out the r squared, and we see that ABC is a plus b plus c minus pi, all times r squared. Now, the r squared is not surprising. The area of a spherical triangle should depend on the size of the sphere. And in a unit sphere, this would just be 1. It would go away. What is surprising is that the area of the spherical triangle depends on the sum of the angles. In fact, you might remember in a spherical triangle, the sum of the angles is always greater than 180 degrees, or in radians, it's always greater than pi. And so if we look at the difference, how much bigger is the sum of the angles than pi? This difference gives us the area of the triangle. And I find that mind-blowing. As a quick example, in our triangle from last time with 3 right angles, that's 90 degrees, which in radians is pi over 2. The area of that triangle is pi over 2 plus pi over 2 plus pi over 2 minus pi, all times r squared. And you can simplify 2 of the pi over 2's with the pi and get The area of the triangle is pi over 2r squared, and that's what we calculated in the beginning because it's an eighth of the whole sphere. So I hope at this point in the series you see that geometry is just a great game to play. It's not the drudgery you might have encountered in school, or at least I did. And one more thing. Do you remember in the plane I had you create the triangle ABC and fix the A and the B and see what other points gave us the same area? That was the challenge where I said find all points X so that the area of the triangle ABX is the same as the area of the triangle ABC. And the result was we ended up with the parallel line to AB through C and through the point that was reflected down the X that was the same height down below. So we came up with two parallel lines. So to me, where geometry gets exciting is if we ended up with parallel lines, what happens in a world where there are no parallel lines? I think the answer is amazing, and I'm not going to prove it here, but I just want to show you the answer, and it's kind of cool. Look for the antipodal points, A prime and B prime, the ones that are on the opposite side of the sphere from A and B. So if A were the North Pole, A prime would be the South Pole. Draw the curve that contains A prime, B prime, and C. This is a curve that we get by intersecting the sphere with a plane containing A prime, B prime, and C. Or we can look at this with the melon, cut the melon so that the knife passes through A prime, B prime, and C without changing directions. So we get something like this. It is not a line. It's a curve. It's not a great circle. But any point on that curve is X, so that the area of ABX is the same as the area of ABC. And that's all we have for now.